All right, it is 9:18, go.
Good morning, everybody. My name is Evan Gunnell, and I'm excited today to talk to you about what I've been able to research throughout the semester, specifically terrestrial rift valleys. And as I've researched, I've come to understand their importance in what I would like to go into for my career, and what I know a number of you are going to go into as well, and that's the petroleum industry. And I will get to that more a little later in my presentation. Just to give you kind of an idea where I want to go with this, I'm going to give you a definition about what a terrestrial rift valley is, talk a little bit about kind of a basic structure and geographic location of where they form. Then I'll move into different factors that can affect deviations from the model, as well as we'll talk a little bit about classification. And then, as I said at the beginning, go into the relevance to the petroleum interest and industry. So, a terrestrial rift valley, what is that? It is a fault-bounded feature, commonly called a half-graben, and it's formed as a result of extensional tectonics. And as you can see here in this figure, we have kind of a before and after. Over here on this side, it's representing the crust pre-deformation. This black dashed line is to signify some kind of weakness in the crust. And then over here, we have what happens, or what you see as a result of extensional tectonics. And this half-graben feature that I talked about in the definition is referring to this wedge shape that forms as a result of the hanging wall being subsided relative to the footwall. And a half-graben is where accommodation space is created and where sediment and water and organics are able to accumulate. This is another model. This one shows not just one fault zone, but multiple fault zones. And as you can see, varying amounts of offset obviously will allow for varying amounts of accommodation space, and thus different amounts of sediment and other things are able to accumulate in the basin fill. And then one last diagram to illustrate this. As you can see, we have the wedge shape again here in the middle. So this up here is a map view. You can kind of see that a very simple model shows that we have kind of a half moon, half circle shape, where up here at B is where you would find the most displacement along the fault. And then as you go out either way, or even out this way, it's going to taper out. And that's better illustrated here as well in this longitudinal section view. If you were to take a slice this way and turn it, you see the beds. They pinch out to the sides, and that would also be happening as it comes out the board. One characteristic of terrestrial rift valleys is what is called tripartite stratigraphy, and this begins with a basin-wide fluvial deposit on the bottom, which is superimposed by a deepening upward lacustrine deposit, and that is in turn superimposed by a gradual shallowing upward lacustrine deposit. So those three together create this tripartite stratigraphic package. As far as geographic location goes, in my research I found that rift basins, these terrestrial rift basins, are found on all passive Atlantic-type continental margins, and they actually form or are there as a result of the breakup of Pangea. So here in orange, all these orange areas are those passive Atlantic-type continental margins. So if you can just imagine all those fit back together as a supercontinent of Pangea, you can kind of see how once rifting would occur, you're going to have it on either side of the rift itself. This diagram illustrates different controls on the type of basin fill within the half-graben structure. Up here on the top, you can see that capacity is slightly less than sediment supply, and sediment supply slightly more than water. So you have an excess of sediment which means your basin fill is going to be dominantly sediment, even with some excess sediment having to be deposited elsewhere. Here in the middle, capacity exceeds sediment supply and water, but it doesn't exceed them both together. So you end up with sediment depositing until it runs out, until the supply runs out, and then the water filling up the remainder of the accommodation space, and even having to find other areas to deposit. And then finally at the bottom, you can see that capacity greatly exceeds the sediment supply, and water also exceeds sediment supply. So you get an even deeper basin fill with water with only a little bit of sediment down here at the bottom. So I talked about sediment supply and water supply as potential causes of deviation from the basic structural model that I showed you earlier. Another big one that I found in my research is basin inversion. And what basin inversion is after a period or an episode of extension has occurred, then it's followed by an episode of compressional tectonics. And what that can do is it can reactivate the normal faults that were there, and they become reverse faults. Also, new reverse faults and thrust faults can form, as well as folding. And I'll show you a picture of that here in a minute. Terrestrial rift valley classification, it's kind of a broad topic, but what I got from all my research is the idea behind classification of these types of basins is to do what you're wanting to do with any model, and that's be able to compare them based on their similarities and differences and highlight the differences specifically. Kingston et al. Was one source I came across, and they spent about 20 years coming up with their classification scheme. And in that scheme, they had 9 major points of classification, most of them relating to petroleum potential within these types of basins. So the relevance to the petroleum industry and interests, I also found that many major petroleum regions in the world are related to these terrestrial rift valleys. And one specifically that I came across is called the Jeanne d'Arc Basin. As you can see in this reference map, it's off the eastern coast of Canada. And then this over here is a cross-section view of the basin. And the Jeanne d'Arc area specifically is drilling out of this pinch-out sandstone right here. And just kind of an idea for scale, this is 10 kilometers, so this portion of the basin is representing 100 plus kilometers of basin fill. And also, as you can see, there are many faults, and you can see some folding, so that the tectonics, the compressional tectonics that I referred to earlier, have greatly affected this basin and have allowed for areas to become good sources and traps for the petroleum found in these sandstones. In conclusion, terrestrial rift valleys are fault-bounded features commonly called half-throbins. They form as a result of extensional tectonics. They are formed on all passive Atlantic-type continental margins, and their classification is meant to create conformity worldwide in the classification of these basins. And then there are many significant oil-producing regions associated in the world with these terrestrial rift valleys. Thank you very much.
Okay, technical questions for Evan.
This is probably a really simple question, but we talked about a deepening upwards and a shallowing upwards. That'd be the same thing as finding upwards and coarsening upwards, or what's the difference?
As far as I could tell with that, it's referring to the actual depth of the lacustrine of the water.
Okay.
So, yeah.
With
would subsidence play a role at anything in this, in sediment supply? I mean, not sediment, but the sediment accumulation?
Definitely, yeah. Along those fault zones, subsidence is going to impact how deep those basins can get for sure. Do you have one?
Yeah, the wells, the pinch outs and the drilling, and can they use almost all of those because the faults aren't permeable?
Some of them, yes. Might be kind of hard to see because it's a little blurry, but these are labeled the actual drill sites that are currently active in this basin. But I know they have found 18 additional sites that they have deemed productive. They just haven't started drilling yet, all in this basin as well.
Faults are very specific. Whoever asked the question, one fault may seal, the next one may not. It's really a risk.
Yeah.
Okay, any other technical questions? All right, comments for Evan